All right, welcome back everyone. This is the second talk of today and the first talk in our focus session on complex and hypercomplex analysis with fractional calculus. This focus session is a pure mathematical topic. Complex analysis is one of the important branches of mathematical analysis, and a lot of work in fractional calculus has been done only in the real setting, although historically complex analysis was important in motivating the original development of fractional calculus in the 19th century. But nowadays, there are not so many people working in both complex analysis and fractional calculus. Therefore, it is useful and interesting to have this sequence of talks that are devoted to this topic. As well as complex analysis, we also have hypercomplex analysis, a general term which refers to more general, usually higher dimensional structures that somehow behave similarly to the complex numbers and on which one can do some sort of analysis. For example, Clifford algebras, quaternions, bicomplex numbers, and so on. There are various different structures on which hypercomplex analysis can be done. And in the last maybe 10 years or so, there has been interesting work coming out relating fractional calculus to hypercomplex analysis in the sense of fractional derivatives in hypercomplex settings, hypercomplex approaches to solving fractional differential equations, etc., as we're going to see in a range of talks over the next I believe 6 weeks, over a period of several talks. So it's a pleasure to start this focus session today with the talk of Professor Nelson Vieira. So Nelson Vieira is an assistant professor in the Department of Mathematics at the University of Aveiro, Portugal, and a researcher at CIDMA, which is the Center for Research and Development in Mathematics and Applications. He received his PhD in mathematics from the University of Aveiro in 2009. His research centers on Clifford and hypercomplex analysis, fractional calculus, special functions, and their applications to differential equations, signal processing, and machine learning. He has published extensively in these fields and held competitive FCT research positions, CECIND 2018, Investigador FCT 2014. He participates in funded projects and serves on editorial boards while reviewing for international journals. And today he is going to deliver his talk on a hypercomplex approach to fractional Helmholtz-type equations. Please, you may go ahead. The floor is yours.
Thank you, Arran, for your introduction. I would like first to thank Arran and Pavan for the invitation to give this talk and to be the one which opened these sessions devoted to the connections between hypercomplex analysis and fractional calculus. Today, as the title indicates, I will speak about the Helmholtz equation. This talk is based on the paper that I published with Milton Ferreira, Manuel Rodrigues, and Zoran Krause. But as you will see, it is connected to other works that I previously published with some of the authors of this, we can say, big work. So, as Arran told, I come from hypercomplex analysis. It was the field where I make my PhD, and after that, when I was in the postdoc, I start to study and to dealing with fractional derivatives, and it came the idea to try to analyze and develop and understand some of the results and facts and theorems that we have in Clifford analysis, not using integer derivatives, because we can say in a simple way that Clifford analysis is it's the theory based on the null solutions of the Dirac operator, but the Dirac operator uses integer derivatives, and we try from now until today to see what happens if we consider, instead of classical derivatives, fractional derivatives. And one of the big importance of Clifford analysis is that we can study in higher dimensions some classical and important equations from mathematical physics. From those that we usually study in this branch of analysis is the Helmholtz equation. And you will see it has, and probably you already know, it has a long list of possible applications. Before that, an outline of the talk. First, the motivation, then some short remarks, some preliminaries on Clifford analysis and on fractional calculus. The part of fractional calculus, it will be more useful to fix some of the notation that I will use. Then I will present the fundamental solutions for the Helmholtz operator. Then the main results about the hypercomplex operator calculus that we can develop. Finally, we will give special attention for the case of separated variables in the three-dimensional case. In this situation, we were able to obtain a graphical representation of our solutions, and we will see that this theory can, in some sense, can be visualized, and our results can be visible in something real. Okay, and then the conclusions. So one of the equations that we have and we study in hypercomplex analysis is the Helmholtz equation. This equation emerged from time harmonic representation of the wave equation, describes the spatial distribution of the fields under steady state wave propagation at the fixed frequency. It has several possible applications, acoustic, for example, electromagnetism, and quantum mechanics. Also, we can also have applications of the Helmholtz equation in acoustic problems, in pattern identifications, and so on and so on. And we can continue here the list of possible applications of this special equation. Under the mathematical point of view, our work aimed to extend, in one hand, the fractional reduced difference transform method that it can be found in the literature, but it is limited to the consideration of only one fractional derivative in one direction. Our work was able to extend this method by the fact that we can consider fractional derivatives in all the directions, and even more, we can have, or we can consider, different orders of differentiation in the different directions. With this, we will, as you will see, we will obtain a factorization of the Helmholtz operator in terms of fractional Dirac type operators, and with we can say with the help of the fundamental solution of these fractional Dirac type operators, we will develop an hypercomplex operator calculus. Then, as I told you, for the particular case of R3, I will present you explicit representations for our solutions. Moreover, I will present you the conditions based on the asymptotic behavior of the Mehta-Clifford function, the conditions that we must impose to our parameters in order to have steady solutions. Also, some graphical representations of our results, and during the talk, I will show you how we can recover some results from classical theory, and also how we can connect our work with another ones involving fractional derivatives in order to see some consistency of our work. So let us start with the preliminaries involving fractional calculus. As I told you, the main idea is to fix some of the notation, because I think almost all the participants are well known, well familiarized with fractional calculus. So we will use the left Riemann-Liouville fractional integral, which we will denote by this. Also, we will use the left and right Riemann-Liouville fractional derivative, which we will denote by this. Also, we will make some reference to the Caputo fractional derivatives, the left and right. Also, we will need some operational properties of our operators. Some of them, you will not see them clearly. They are used in the proof of our results, but I put it here, one of the ones that we use, namely the composition rules between fractional integrals and fractional derivatives. Also, as you will see, our solutions, fundamental solutions, will be represented in terms of Mehta-Clifford functions, more precisely the two-parameter Mehta-Clifford functions, which we already know is defined by this power series. For this special function, we have the following asymptotic behaviors near the origin or in the infinite. And these two relations are very important in the last part of the talk in order to obtain the conditions over the parameters and in order to understand the behavior that we see in the graphical representation of our solutions. And now the part from Clifford analysis. I put it here only a very short introduction. We can say much more about Clifford analysis and hypercomplex analysis, but in order not to overload the talk, I put it here only the basic facts that we need. So we consider the Rn vector space with the orthonormal basis, and we define the universal Clifford algebra as a 2 to the power n dimensional associative algebra, which obeys to this anti-commutative rule, yes. And here we have the Dirac operator. We can say, as I told you, it's the basic or the basic stone in some sense of Clifford analysis. And this operator, by these multiplication rules, we can prove that factorize the Euclidean Laplace operator. And this is very important because now one of the main difference that we have from Laplace to Dirac, it's in the Dirac we can give a direction, for example, for our derivatives. And in some sense, the property of factorization, it's very important because allow us to develop an operational convenient calculus. Also, we have here the representation of any function in R0n. Important to refer that properties such continuity or differentiability have to be understood component-wise. And let us now combine these two areas, fractional calculus and Clifford analysis, to study the Helmholtz equation. The expressions, as you will see during the talk, are not very nice. The most important that I want you to be able is to understand the message of the results that we are presenting. If even more, but if you have any question, please in the end make the one. So we are considering the Helmholtz operator and the first order translated Dirac operator defined in this way. What we already know from the theory of Clifford analysis, that the fundamental solution of the Helmholtz operator is defined by this expression, depending on the nature of the image part of the parameter length. The expression of this fundamental solution, we have here the surface area, and here we have the Hankel functions, which, as we know, which are defined or can be written in terms of Bessel functions of first and second kinds. Our fundamental solution has important properties. It behaves like the fundamental solution of the Laplacian near the origin. When the argument goes to infinite, we have the following asymptotic behaviors, and in distributional sense, we have we can say the relation that guarantee us, one of the relations that guarantee us that this function is in fact a fundamental solution. So what we can do now, and this is typically what we do in hypercomplex analysis, we have the fundamental solution of the Helmholtz operator. We apply the Dirac operator to our solution in order to get the fundamental solution of the Dirac operator, this translated Dirac operator that I introduced previously. So applying the operator, making some calculations using the properties of the Bessel functions, and we arrive to this expression for the fundamental solutions of the Dirac operator. Where, as you can see, we have some repeated elements, the surface area, we have the Hankel functions that appear in the previous expression. Here also, I consider here the operator, I only presented here the fundamental solution for one of the operator, but if we replace here by minus lambda, we get the fundamental solution for the other operator. Now, let us pass to the fractional version of this operator. To do that, we need to fix some notation. As I told you, not a nice notation, but most important, understand what is happening. So we consider a bounded open rectangular domain. Here we have you can say the vectors of orders of differentiation in each direction. We consider the fractional Laplace operator defined in terms of left Riemann-Liouville fractional derivatives in each direction and associated Dirac operator. They are the same that I presented previously. What we have done, we have replaced the integer derivatives by fractional derivatives. In this case, the left Riemann-Liouville fractional derivatives. We proved in the paper that under specific conditions, the factorization property that we have in classical Clifford analysis remains in the case when we are using fractional derivatives, which is very good and convenient for us. Also, it is convenient because we can reproduce some of the process that we already know in the classical setting. Moreover, we need to consider this variable x hat, which is nothing more than the initial one, but we omit the first coordinate, the first element, x2 to xn, and the correspondent operators with the same starting at 2 and here started at 1. Okay. So how we start this process of developing our hypercomplex operator calculus? We start solving a Poisson problem. So assuming that these conditions over the unknown function v and the right-hand side u, and also assuming this fact on the fractional derivative of v with respect to the first to x1. So we can prove that using the Laplace transform that the solution of this Poisson equation is given in the operational form by this expression, where the functions f0 and f1 are given by this. And what we have done after we proved this result, we consider it as a right function, the delta function, and we obtained the fundamental solution of our fractional Laplace operator defined in terms of left fractional derivatives, Riemann-Liouville fractional derivatives. And also it is given in this operational form. These expressions can be this expression can be simplified if we consider more restrictive conditions over the function, the unknown function, but we prefer to present in this paper the most general situation, where f0 and f1 are given by these expressions. First remark, if we consider the limit case of the order of differentiation going to 1, we recover the fundamental solution of the Helmholtz operator, the one that I presented initially, and the functions f0 and f1 become the following ones. And now we have the solution. We have studied the Helmholtz operator. Let us pass to the fractional Dirac operator, the associated ones, the translated. So for our operator, we can factorize it as with these two Dirac operators, one, of course, minus lambda plus lambda, assuming also that we have the semigroup properties that allow us to prove this factorization property. And like it is usually done in hypercomplex case, now we apply our fractional Dirac operator. In this case, I consider this one to our fundamental solution of the Helmholtz operator, the fractional Helmholtz operator, and we get the fundamental solution of the fractional Dirac operator with lambda. And this is what we have done. We applied our operator, making some calculations, quite technical, but not too difficult. We arrive to this expression for our fundamental solution, where for in the first component we have this expression, and for the remaining ones we have this expression, where the functions f0 and f1 are given by this expression. Moreover, and like I told you previously, this, if we make the limit case of the previous expression, we recover the solutions that we already know from classical Clifford analysis, which show us that our results are, in some sense, consistent and generalize what it is known from the classical theory. Now, what is important if we want to develop an operational calculus? As you will see, these operators will be integral operators, which will be defined in terms of our fundamental solutions of the Dirac operator. So it will be necessary to prove that our fundamental solutions are L1. Otherwise, our operators will be not well defined. And this is what we have done after we get the expression for our fundamental solution. We proved that our functions are in fact L1 functions. If the functions f0 and f1 satisfy these two conditions, and this is the fundamental solution for the Helmholtz operator, the fractional one, these four conditions, if we want to guarantee the L1 integrability for the fundamental solution of the Dirac operator. Here, it is a misprint. It should be Riemann-Liouville. But as I will tell you in the end, in some slides, all the results can be obtained either for the Riemann-Liouville or for the Caputo case. So, and this is the slide one. All the results that I presented previously for the Riemann-Liouville case can be presented for the Caputo case. And you can see these two situations in our paper, which is the basis from this presentation. Also, if you consider lambda equal to 0, you get the fractional Dirac operator, and we already studied this operator in the previous paper, and we showed in this one that we recovered the results that are presented here also. And if even more, if you consider lambda equal to 0 and n equal 3, you can also recover the results. Not all, because in these two papers, me and Milton only obtained the expressions for the fundamental solutions, but you can see that you can recover also here the expression. So the results that I presented you have a quite general nature. And so now that we have our fundamental solution of the fractional Dirac operator, d lambda, we can now, and we proved that this fundamental solution is L1. Now we can start developing an analogous of the operator calculus that we have in classical Clifford analysis for this fractional setting. And this is what we have done. We start proving a fractional Stokes formula. And here, as you can see, and this is one of the big, we can say, big difference from classical Clifford analysis. Depending on the operators, because here in the proof you use the integration by parts, and this fact show us a very interesting fact that, contrarily to the classical case where we have only one Stokes formula, what we have here, we have a triple duality. In the same fractional Stokes formula, we have Riemann-Liouville and Caputo fractional derivatives. We have right and left derivatives, and we have operators with plus lambda and minus lambda. And this is something which is very different from the classical case. In fact, we can present not one, but 8 different Stokes formula for this fractional setting. However, if you consider lambda equal to 0 and alpha limit case alpha equal to 1, you recover the classical Stokes formula that we have from Clifford analysis, classical Clifford analysis. Also, as a consequence, we have a fractional Borel-Pompeiu formula, and even more, we can get a fractional Cauchy integral formula for our case. With this, we have now our operators. We can define now the fractional analogous of the lambda Teodorescu and lambda Cauchy-Bitsadze operators. which are convolution operators, where we have here our fundamental solution. This is why it was very important that to prove that our fundamental solutions were L1 functions. With these operators, we can present an alternative formulation of the Borel-Pompeiu formula. And now we can prove some important properties of this integral operator, which are useful to solve boundary value problems. Usually it's the most important application, indirect application of these properties. First, we can prove that our lambda T operator is the right inverse of the fractional Dirac operator. Also, we can introduce this fractional Sobolev space with this norm. Here, let me take your attention to tell you that when beta, it's all the entries of beta are integer numbers, we recover the classical Sobolev space. In the next results, we have this notation. Please take into account that because these symbols will appear in the index of our space. So what we can prove that our lambda Cauchy Bitsas operator maps functions from this space to the kernel of our fractional Dirac operator. Also, we can prove that the fractional lambda T operator is bounded from this space to the LP to LP with P in this range. And also we can prove that the fractional lambda T operator is a continuous operator. And also we can prove that the lambda F operator acts continuously on this space. And we can say one of the most important results that we have in our paper, it's the following Hodge decomposition, where we present a direct decomposition of the LQ space, where Q is given by this expression, where P belongs in the same range as in the previous results about the properties of our operators. And also associated with this decomposition, we can define the correspondent projectors. And as I told you, one possible application of these operators is in the resolution of, can be found in the resolution of this problem, where the solution is given by the composition of these fractional operators. Also here, we prove in our paper that when in the limit case of integer derivatives, all the definitions reduce to the correspondent ones that can be found in the book of Gurlbeck and Sprosik. And when we consider lambda equal to 0, we get all the previous results that we obtained only for the Dirac operator. And now, let me see the time. Okay. Let us focus our attention to the case, the three-dimensional case, the separation of variables. So we restrict our calculations to this domain. We will have three orders of differentiation, alpha, beta, gamma, and using the method of separation of variables, we can prove that the null solutions of our lambda fractional Riemann-Liouville operator, each of the components, it's given by this expression, and as you can see now, the expressions are much more simple than the previous one. And also from this result, what we can do, we can make a graphical representation of our components function. In this case, we have the representation of U1. And when we wanted to do that, we wanted to present the cases where we have steady state solutions. In other words, solutions that do not blow up when x goes to model of x goes to infinity. And we realize when we were making the numerical simulations and the graphical representations, we realized that it was necessary to impose some conditions over the parameters. And initially, we got some representations, but we conjectured that which were the conditions that we need to impose. We obtained the graphical representations of U1, U2, and U3, and with these conditions, we get, in fact, steady state solutions. As you can see, we have when x goes to infinity, U1 goes to 0, and different values of the parameters mu and alpha change the shapes of our functions. The same occurs for U2 and also for U3. But now it was necessary to clarify if these conditions were correct and how we can prove that. And this is where the symptotic behavior of the Mehta-Clifford function, it's very important, because allow us, and I will back here, allow us to prove that the conditions that the numerical simulation suggested was corrected. In fact, in order to have steady state solutions, we need to impose conditions to our parameters. And this is where we got the conditions that I already wrote it previously. Here it's even more restricted condition to lambda. Let me show you also, we make here the plot for, we assume it here that z is equal to 1. So we have the product U1, U2, U2, U3. Here we assume that x was equal to 1. And also here we have solutions which are steady state. And this was a very important result because, as I told you, because it was possible to verify analytically what it was given by the graphical representations. Also here, in order to show that the conclusions were correct, we consider parameters that do not satisfy the condition, and as it was predicted, we get a non-steady state solution. So, I mean functions that blow up when we go to the infinite. So our conditions were correct theoretically, and in practical were correct and give us behaviors that was predicted by us. Also here, if we make the limit case of the order of differentiation, we get the components of the classical solution of the Helmholtz equation in R3 by the method of separation of variables. Also here we can indicate that we have consistency in our results. And with that, with this, what we can do even more, we can get the fundamental solution of the fractional Helmholtz operator lambda lambda RL with left fractional derivatives given by this expression, and our fundamental solution is also, we proved that it is LL1 function, and also that satisfy the conditions that are expected for the fundamental solution when we go, especially when we go to the infinity. Okay. Conclusions. Our work extended models that we already know from electromagnetic oscillations. As I previously told you, we have the advantage of considering fractional derivatives in each direction, in each variable. We have a set of solutions, and even the set of steady-state solutions are much larger than the ones that we already know. We explicitly compute fully analytical the fundamental solution for the complete subset of all separable solutions in R3. This allows us to understand the symptotic behavior of our solutions, and we were able to classify totally the steady state and blow up cases in terms of the parameters lambda and all the parameters that appear in our Mehta-Clifford functions, which it's something very useful and important. Here I put some of the reference that we indicated in the paper. Here are the works that are connected, the first four with our work directly. Here I put some reference, as I told you, not all the ones that we have in the paper, but some reference that I think are important. Some of them here in the part of Clifford analysis. We can say the classic books, some of the classic books. Also here, of course, you'll know some classic books of fractional calculus. Here, this paper is very important because it's a paper where you can find the fundamental solution of the Helmholtz operator, the classical one that I presented in the beginning of the talk, and more books also from the classical fractional calculus. And thank you for your attention.
Thank you very much for this nice talk. Do we have any questions or comments from the listening participants? Yes, Pavan.
Thanks for the interesting talk. I wanted to understand the details of this fractional Stokes theorem because I was looking into it on a vector calculus perspective and perspective. So I wanted to understand why do you have the two operators?
Because if you see the proof in the paper, you can start with one of the derivatives, Caputo or Riemann-Liouville. What happened during the proof? There will be a part where you will need to apply integration by parts, and when you do that, what it would happen? If you start with the Caputo derivative, you will have the integral, and inside the derivative, correct? But when you do the integration by parts, everything will change of position. So you will pass the derivative outside the integral. So you will have the derivative of the integral, and you get the Riemann-Liouville fractional derivatives. This is the moment where everything changes.
Okay, so
in the case, let me finish. And when the situation of the lambda and minus lambda, you first make the proof without the lambda, then you add and subtract the lambda, and this is where it appears the minus and the positive lambda. It's I don't know if You understand?
No,
But
I understood I understood because that integration of parts formula I'm acquainted with it. For the fractional derivative, if you start with the Caputo, you have the left sided will give you a right sided as well. So that part I'm acquainted with. Uh, okay, so but
Let
okay,
me also
within
add, just for the benefit of Pavan and the people who maybe haven't studied this hypercomplex analysis, that as far as I understand, we are in a non-commutative setting here, and therefore the derivative operator can be applied either on the left or on the right of the function, and these two things would be different. And in this formula, you can see the Riemann-Liouville derivative is on the right of f, and the Caputo derivative is on the left of g. So this is another sort of lack of symmetry that maybe contributes to the complexity of the equation.
Yeah,
thank
that was
you.
going to be my second question actually. But then what would because I'm having difficulty in understanding like okay then what would be, let's say, what would be the divergence if I have to somehow define this kind of an operator and what is even the physical meaning of it. Uh, because I mean those are fundamental objects for studying physics, divergence and the curl of a vector field and so on and so forth. So
If
it's a little
in terms of differentiation, it works equally. The the divergence, the difference is where you have the basis. If it is on the right, on the left, but the way it works, the part of the differentiation is the same. But I forgot to tell during the talk because probably I'm used to, and I assume that it was clear, but it is different in Clifford analysis when you apply the operators from the right or from the left. Because you have the position of the basis, and if you remember in the beginning when I show you the multiplication rule, we have an anti-commutative situation, but in terms of differentiation, doesn't change.
okay. Okay, okay, possibly okay, but okay. My question. Okay, okay. Thanks. That's nice to know that technical part as well. But okay, if I want to define a differential operator and I see there is like a two functions f and g, so will they form the part of the definition of, let's say, the grad kind of an operator, or like let's say there is a linear operator equal to something. So those f and g are part of the definition of the operator.
No, this is functions where you apply the operator.
Okay. So it's like, okay, you have a vector field, which is like, let's say, uh, P I cap plus Q J cap in two dimensions. That's it. And I have a differential operator. And so it's like the differential operator acts on P. So that's one function, let's say F in here. What is G? Where is G coming from? Sorry if my questions are a bit uh, idiotic, but
Trying to understand what you are asking. So you have the operator. You have you have the Caputo operator, which is EJ and the fractional derivative. Then you have the function with the components. So you operate and also the function will be defined in terms of components. When you apply the operator, you make the calculation over the elements of the basis, and then you apply the derivative.
okay.
If I understand your question.
Possibly, I think so. I am checking the statement, uh, uh, and F and G are absolutely okay. So I think so. I think so. I understand now what F and G is possibly. So might as well look into the paper and check for the details. And but thank you. If I have questions, I'll probably come back.
No, don't worry. Now it will be good to have a whiteboard to make the.
Yeah, actually, because it's just it would be much easier to just like okay, this is it, this is it, this is, and that's it. Yeah. I looked into it as well. I looked into it as well as a part of the development of my machinery for deriving fractional conservation law. I presented in this talk in this seminar series last year, but hopefully I'll start writing the paper and send it out.
All right.
Thank you. It was kind of interesting.
Any more questions, comments from others? I actually wondered something. If you go to equation 11, you have this E function, which I believe is not related to Mittag-Leffler, right? This is a function using Bessel.
No.
And this
It's
is for the
not
non-fractional case. Then when you go to the
Yes.
fractional case, you get a Mittag-Leffler function appearing, right?
Here?
I mean, the fractional version of this result in equation 11 involves some Mittag-Leffler functions.
Okay, why we have that? It was during the now I get it. You are asking why we do in the classical case we do not have, but you have a series also there in the classical case. But what let me remember all the proof that we have done, because also you have series in both sides. But this is an operational form. Also, we cannot forget that in the other case, it's a form. I understand your question, but if you restrict to the other case, you should get, and I think we have made this proof also, you get the uncle function, making a proper choice of the functions f0 and f1. But it is possible.
Okay, because often in fractional calculus, we see the Mittag-Leffler function appearing as like a fractional version of the exponential function. But now you have Mittag-Leffler as like a fractional version of this Hankel or Bessel related function, which is interesting. There's another relation maybe.
Yes, we do. The way you are making the interpretation, I don't think we saw the things in that, but it seems interesting.
But I suppose in the fractional version, if you set the fractional order to be 1, then it would come back to this version with the Bessel functions, right?
I'm trying to recall the calculations. We make a lot of calculations. I don't. My memory is failing, but I think we proved that. Yes.
Okay. Oh, interesting. Thank you.
But it's not fresh how it was. But we make several verifications of the consistency. Usually, the one that we use is to see that making alpha equal to 1 will recover all the results that we have in the classical analysis.
Yeah.
But it should be something also very tricky. Usually, it's not something that it follows directly. You need several times to make manipulations and so on.
Yeah, I can see you had a lot of difficult manipulations in this work. Okay, thank you. Any other comments, questions? Yes, Milton.
Hello.
Hi.
I just want to remark that the question of Pavan about the Dirac equation. So for instance, in n equals 3, the Dirac equation encodes both the divergence and the curl operator. So if you apply the Dirac operator in 3-dimensional case to a vector field, it's composed in a scalar part plus, let's say, a bivector part. The scalar part is the divergency, and the bivector part is the curl. Then If you go to higher dimensions, you have something of this, but generalized. You have always a scalar part, which is a divergence, and then some generalized curl operator. If you go to multi-vector function, so I said only a vector function, but then if you go to the all Clifford algebra, to a multi-vector function, then you have lowering and raising operators inside the algebra. So the scalar part do a lowering part, so it's some kind of divergency, and the bivector part will give a raising. That's a generalized notion of divergency and curl, but to multi-vector function. So just to quote, the Dirac operator encodes both divergency and curl operator. That's why it's a fundamental operator, because it's in one single equation you encode these two operators.
Thank you very much. I did not know about the Dirac operator, so I had those type of questions. But thank you very much for sharing the knowledge. I think I will go back and look in more detail. This was very interesting to learn about Dirac operators as well for me. If you have some, if you have some good references, please let me know. Oh, sorry.
If you apply the Dirac to a real function, it is a gradient. If you apply it to a vector function, then, as I said, you already see these two operators. And then you have also the possibility to apply it to a multi-vector function, so a function with all components in the Clifford algebra, which is a generalization.
Okay, but it sounds like very close to the del operator in classical vector calculus. Is there any? Is it a further generalization of it?
Which generalization?
The Dirac operator. I think I will have. I think I'll have to look into it. I'm getting lost in a bit of terminology, but thank you for sharing that knowledge.
Okay, you're welcome.
It was very nice of you.
Thank you, Milton. It's clear that I didn't understand the question of Pavan. But now I understand what you were asking, and it's perfect what Milton told.
Thank you.
Okay, thank you. Any more comments, questions from anyone? If not, then once again, thank you very much for the talk, and we will close the recording and the session here.